Scientists today are running some of the most mind-blowingly complex simulations you can imagine. Things like turbulent fluids, even colliding galaxies. But these simulations create this titanic problem. It's a tsunami of data so huge, it's actually threatening to overwhelm our ability to even store it. So in this explainer, we're going to dive into a brand new technology called ANTIC, which was built to solve this exact crisis. Just look at this. I mean, wow. This is a simulation of two black holes spiraling into each other and merging into one. And this isn't some artist's cool idea. No, this is the result of solving Einstein's equations on a massive supercomputer. We can literally model the fabric of space-time itself. But as you can probably guess, it comes at a pretty steep price. And that's the billion-dollar question, isn't it? That's what we're really digging into today. High-performance computing has given us the power to generate these just incredible insights, but it's also created this massive data storage bottleneck that's threatening to grind progress to a halt. Okay, so to really get why the solution is so clever, we first have to wrap our heads around the sheer scale of the problem. And we're talking about numbers that are, well, they're almost hard to fathom. Remember that single binary black hole simulation we just saw? Just one run of that simulation generates 4.2 terabytes of data. To put that in perspective, that's like filling up 4 or 5 brand new, top-of-the-line laptops completely full just to store the result of one single experiment. And here's the thing. It's not just astrophysics. We're seeing this in computational fluid dynamics, plasma physics, climate modeling, you name it. They're all generating data on the scale of petabytes and, believe it or not, even exabytes. And just so we're on the same page, a petabyte is 1,000 terabytes. An exabyte is 1,000 petabytes. The numbers are just staggering. And this, right here, this is the heart of the problem. Our ability to compute things is growing exponentially, but our ability to actually store all the answers we're getting, it just isn't keeping up. It's creating this huge traffic jam for science, and it's this exact bottleneck that ANTIC was designed to completely shatter.
All right, so how in the world do you solve a data problem that seems impossible? Well, you don't just throw more hard drives at it. You get clever. ANTIC, which, by the way, stands for Adaptive Neural Temporal In-Situ Compressor, tackles this with a really brilliant two-pronged strategy.
Now, the very first thing to notice here is that ANTIC is an in-situ compressor, and that is so important. It means it doesn't wait for the simulation to finish. It works right there, in real time, as the data is being generated. And that's absolutely essential when you can't even afford to store the raw output for a little while. So, ANTIC's strategy, in concept, is just elegantly simple. First, it looks at the simulation over time. It acts like a smart film director, deciding which frames of the movie are actually important enough to keep. Then, for the frames it decides are keepers, it compresses the space, the actual 3D snapshot of the data, with just incredible efficiency. So let's dig into that first step, picking the right moments. How does ANTIC know which moments are the important ones? This isn't just, grabbing every 10th frame or something. No, this is about actually understanding the physics of what's happening. And this right here, this is the brain of that whole operation. It's called the Physics-Aware Temporal Selector, or PATS for short. And its whole job is to watch the simulation evolve, and at every single step, it asks one simple question. Is something scientifically interesting happening right now? So PATS breaks this down into 4 parts. First, you've got the metric. That's the core. It's basically an interest detector. For fluids, it might track turbulence. For black holes, it tracks gravitational waves. Essentially, it's a little flag that goes up when things get chaotic. Then the Q holds a short-term memory of what that flag has been doing. The regulator then cleverly adjusts how far back in time it's looking. And finally, the gate makes the call based on all that info. Save the snapshot or toss it out forever. And this just explains the result perfectly. Think about it like a camera operator at a sports game, right? You don't record the entire game. You record the highlights, the goals, the dramatic saves, the near misses. PATS does the exact same thing for physics. It saves tons of frames when things get chaotic and interesting, and then barely any when things are calm and, well, boring. Okay, so ANTIC has picked out all the highlight reel moments, but each one of those snapshots is still massive. So how does it shrink them down? Well, this is where the second part of its attack comes in, and this one is powered by AI. So the core tech here is something called a neural field. And honestly, the analogy on the slide is just perfect. Instead of saving a huge voxel by voxel 3D image of the data, you train a tiny little neural network to perfectly represent that image. You don't store the painting, you store the tiny artist who can repaint it for you perfectly whenever you ask.
Now here's where it gets even more clever. Training a whole new artist for every single snapshot would still be way too slow. So ANTIC uses this technique called continual fine-tuning. Basically, the artist from the last saved frame doesn't start over from a blank canvas. It only has to learn the changes, the difference to paint the new frame. It's only learning the residual, which is a much, much, much simpler job for a neural network.
So let's just put this side by side. The old way, training from scratch, is super slow and inefficient. But this new way, continual fine-tuning, is over 10 times faster at getting to a solution just because the problem it's solving is so much easier. And that speed is absolutely critical for an in-situ tool that has to keep up with a live supercomputer simulation.
So you've got this smart time selector and a hyper-efficient AI compressor. What happens when you put them both together? Well, the results are, frankly, they're just jaw-dropping. Just take a look at these numbers. For a really complex 2D fluid simulation, ANTIC got a compression ratio of 435 to 1, but for that massive 3D black hole merger, it achieved a compression of over 6,800 to 1. I mean, come on, that's not just an improvement, it is a revolutionary leap forward. Let that number sink in for a second. 6,807 times smaller. That 4.2 terabyte simulation we keep talking about, ANTIC can shrink it down to a file size that could fit on a cheap little USB stick you have lying around. It's insane.
And here's the proof in the pudding. These gorgeous images, these aren't the originals. They are the high-fidelity reconstructions that were generated from that tiny, tiny compressed file. Visually, and way more importantly, scientifically, all the critical information is still there. And this might be the most crucial takeaway of the whole thing. This extreme compression doesn't destroy the science. It's not lossy in a way that matters. The researchers showed a reconstruction error rate as low as 1 part in 100,000. That means the data is still totally trustworthy and completely useful for scientific discovery. So, by being super smart about what to save and using AI to be incredibly efficient about how we save it, ANTIC has basically just shattered one of the biggest barriers in modern science. And it just begs the question, right? Now that we're not limited by the size of our hard drives, what new frontiers of the universe are we going to simulate? And what are we going to discover next?